Hey guys.
Yo.
Yo.
Hey, Catch.
What's up? Okay. All right, I am now officially recording. I forgot to do that, so let me just repeat myself real quick. Today's topic is the fundamental theorem of calculus. Cool. All right, so here it is. The fundamental theorem, in my own words, says that when we take the integral from a to b of f of x dx, so of any function, here's how we actually solve it. And we've done this on our calculator to get the exact answer. We've estimated it using Riemann sums and a trapezoidal sum. But today we're going to do this by hand algebraically to get the exact answer that our calculator does. So we have to take the antiderivative, which is capital F. And then there's going to be a new notation that I'm going to show you. And it's this line here. And at the top of that line, we're going to put our upper limit. And at the bottom part, we're going to put our lower limit. So B and A.
Mr. Maj, is that a B or a 6?
It's a B.
Okay.
It's this and this, B and A. All right. So what does that mean? It means that we have to find big F of B and subtract big F of A. Hey, Tim. All right, that's what that means. That line there with B and A. Now, what is large F? What is capital F? That is the antiderivative of little f. So these couple things have to hold true. Big F is the antiderivative of little f. So it essentially means that if we took the derivative of lowercase f, we would get capital F. That's what that means. And then also our function f of x, little f of x, needs to be continuous. So f of x has to be continuous. At least from a to b. If you're not continuous, then you can't have an area underneath your non-continuous curve. You know, you might be shooting off to infinity, you might have a hole or a jump. So we couldn't take the integral anyway. So we do have to make sure that our function's continuous on our interval from a to b. And remember, a and b, a is the lower limit and b is the upper limit. All right, this looks a lot more complicated than it actually is. Once we do a couple examples, you'll see that it's really not too conceptually difficult. The most difficult part is just not messing up the algebra, which is why I recommend having this handy dandy tool to check your work, make sure you do it right. All right, I'll give you a second to copy that down, and then we'll go on to some examples. Okay, I'm going to move on to the first example. I can go back to this page if you need me to. Okay, so we basically just want to evaluate all of these. So the directions are just to evaluate. We just want to find a single number. So our first one, this is something that we did the other day. We were looking for the definite integral. So again, this is called a definite integral because we have numbers here. We have limits of integration. So we won't need a plus c ever. This is going to be a numerical answer. And we wanted to find the area underneath the curve of x squared. So we did this the other day. You don't have to draw this, I'm just reminding you what we did. We went from 0 to 1 of x squared. And it looked like this. So we were essentially finding the area underneath x squared until 1. Does anyone remember what that answer was from the other day?
1/3 x cubed.
It was just 1/3 was the final answer. But you're right, Stallings, that's going to end up being the antiderivative that we'll use to find that answer.
Okay.
So when we found this on our calculator, it was 0.3 repeating, which means that this area underneath the curve of this is y equals x squared right here from 0 to 1, that's 1/3. So we found that on our calculator and we estimated it using Riemann sums, but now we'll find the exact answer. So our fundamental theorem of calc says we need to take the antiderivative of x squared, which we just established was 1/3 x cubed. Now we don't need a plus c here because this is a definite integral. It has numbers here. If there were not numbers here, it would be a more general antiderivative and we need a plus c to account for any random constant at the end. But we don't need that because it's definite. And then we need to evaluate this at 1 and at 0. So we're going to put that little notation there, that line. And that means that we're going to first evaluate this function at 1. So I'll do some colors here so you can see. So we'll do this one in green, this one in blue. So I'm going to plug in 1. So I basically just evaluated this big F function at 1 first. So I plugged in 1. Then I'm going to subtract and evaluate that at 0. So 1/3. And then I'm going to plug in 0 cubed. Okay, now this is definitely PEMDAS. You have to be careful with your order of operations. In this case, it's not going to really matter that much if you mess up order of operations because these numbers are nice. But we do want to first do our exponent. So we're going to do 1 cubed first, which is 1 times 1/3. So that gives us 1/3 in the first parentheses minus over here, 0 cubed is 0 times 1/3 is still 0. So our answer is 1/3. So that means that the area underneath the curve y equals x squared from x is 0 to where x is 1 is 1/3. That's this area in here. And we couldn't find that geometrically because this is not a triangle or a rectangle or something that we can easily find geometrically. It's literally curved. And so we need to use calculus and the fundamental theorem of calc to find it out. So on your calculator, to double check, you hit math 9, and that gives you the integral symbol from 0 to 1 of x squared dx, and you will get 0.3 repeating, and that's how you can check to make sure you did this right. Your calculator will let you know. Pretty cool. Okay, questions on that one? Okay. Let's do our next example. I just have a bunch of examples today. We're just going to run through them. Here's something I forgot though on that page. We forgot to check for continuity. That was a big thing. So we want to make sure that this function y equals x squared is continuous on the interval from 0 to 1. Well, since y equals x squared is just a quadratic, it's just a polynomial, it's continuous everywhere. So we could, in fact, find the integral here. Okay. Okay, our next one, I'm going to just swap the limits of integration. So I want you guys to try this one. It's the same thing, basically, except you're going to subtract in a different order once you do it. So try this one, writing it out. Integrate, plug in 0, subtract, plug in 1. It's too quiet. I unmuted you guys.
Hi.
Hi. So what I like to do for plugging in each value, I know this one seems obvious, but we'll just get -1/3 in the end. But for plugging in each like upper limit and lower limit, I like to put them each in their own set of parentheses with the minus sign in between, kind of like separate each as a distinct number, and then we'll subtract at the end. All right, so all this did was swap around the order. So this is still 0, and the other one was 1/3. But when we swapped the order, we ended up getting a -1/3. I wanted to point this out because on the previous page, we did this. We got +1/3. So what happens when the only thing we change, note what happens when the only thing we change is the limits of integration. We swap them around. We end up just getting the opposite result. And that holds true. That's like integrating from left to right and then right to left. The end result ended up being swapped. Okay, one that's a little more complex. Let's do the integral from 1 to 3 of 3t squared minus 1/t dt. So we want to ask ourselves, is this function, this entire integrand here, is this continuous everywhere? What do you guys think?
Negative.
Yes. Wait. Maybe not.
Hard to say.
Not at 0.
Why not at 0? Was that Ryan?
It's got a t in the denominator.
Yeah, I agree.
So
with
this just
That's not
3t
gonna
squared
matter.
by itself would be continuous everywhere, but when we throw in the 1/t as part of our function, we can't plug in 0 because we can't divide by 0. So
That's not gonna.
Yeah, it doesn't matter.
Yeah, you're right. It does not matter for this because 0 is not a part of this interval here from 1 to 3. So I'm just pointing out our thought process. Even though this function here is not continuous everywhere, it's continuous from 1 to 3. So we can proceed. Nice job. Okay. Let's take the integral of 3t squared. So it would be just t cubed because we'd end up getting 3/3. And then remember, you can always check to see if you found the integral correctly by just taking the derivative. So if we took the derivative of t cubed, we'd get this. All right, what is the integral of 1/t?
ln of t.
ln of the absolute value of t. So this is t to the -1st here, if you were to rewrite it. And that's the only exponent that doesn't follow that backwards power rule like this. if you have 1 over x or 1 over t or whatever, it's ln of the absolute value of that. So we want to, I'll do this line in a different color so it doesn't look like the absolute value line. We want to evaluate that from 1 to 3. So we're going to first plug in 3, put a subtraction symbol, then plug in 1. I'm going to put the whole thing for 3 in parentheses, and then the whole thing for plugging in 1 in parentheses. So we'll have 3 cubed minus the natural log of 3. I don't need absolute value anymore because 3 is positive, so you don't need to put like the absolute value of 3 because it's already positive. Then when we plug in 1, we'll have 1 cubed minus the natural log of 1. All right, so this is 27 minus ln 3. And then it's going to be minus 1. Question of the hour. What's the natural log of 1?
0.
0. Nice.
I'm so freaking smart.
Who was that?
Boy, Kyle.
What do you think?
Oh, hey, Kyle.
Oh, Kyle Cook.
Good joy.
Remember what this means, guys, is e to the what gives us 1. E to the 0 gives us 1. That's why the natural log of 1 is 0. All right. ln of 3, I don't know. We're just going to keep it like that because that's not like a special one that gives us a nice answer. So our final answer, 27 minus natural log of 3 minus 1, right? Because it's just 1. So our answer is 26 minus the natural log of 3. We're going to assume this was a no calculator problem, so we can just leave it be. If you checked this in your calculator, it would obviously give you the decimal equivalent, which you could just check by plugging that in too. Cool. What do we think about this so far?
Light,
About
light work.
Fácil, difícil, o así?
Facile.
you.
Not too bad.
Bless you.
It's insanely easy for a
Big.
brainiac like me.
That's good. That's good.
I have no idea why it is the way it is.
Why what?
Don't understand why this works. Really.
Why it's so hard to hear. I'm sorry, Ryan. One more time.
I don't understand why this works.
Oh, why this works. Because you're taking, so you're going the opposite way. To be honest with you, I'm not going to give you a great explanation because I would have to think about it a little bit more, but you're essentially finding the area underneath a curve. And so this is the height, like if you were to draw it. This is like not a great function because it's so complicated. I'll go back to the easier function to explain it. But you're essentially trying to find your Riemann summing an infinite number of rectangles. And so those rectangles look like this. And when you have an infinite number of them, they're so tiny that they basically do give you, they don't really over or underestimate anymore because you have so many of them. And so a rectangle is base times height, right? So this is the height. X squared is the height because it's your y value. And then dx is like delta x basically. It's called the something of integration. I can't remember exactly what it's called, but it means the distance between your two x values that get smaller and smaller and smaller. So you're essentially adding together or summing all of those areas of rectangles from x is 0 to x is 1. That's the main idea behind it, is it just infinite amount of Riemann sums over and over. Why the antiderivative works at this point, I don't know. But I do know that you're essentially finding an infinite number of rectangles. And so this is really just a glorified height times base from a certain value to another value. Somebody that is a lot smarter than me could explain that probably better to you on YouTube if you want to search it. But that's what I got for you. So I hope that answered like at least 1% of your question. But that's essentially what we're doing. Okay, that's what that dx is anyway. Constant of integration is what it's called. There you go. Okay, but yeah, that's just delta x. It's like distance between your x values. All right, let's go to another example. All right. I don't know which one we're on now. Let's see, 1, 2, 3. Example 4. It's going to be the same function from -1 to 1. All right, get this one written down.
How are we going to be able to take an integral of this?
Good question.
It isn't continuous, is it?
You're right. So we can't do this one
Let's go, Art.
because this function is discontinuous at t = 0. And since t = 0 is on this interval, we can't take the area of it. Basically, if you were to graph this, there'd be an issue at 0. So there's no way to find like an area under it since we're not continuous there. Cool.
Okay.
That one does not have a solution. Good job.
Nice catch, Art.
Thank you, Chandler. It means so much, bud.
Let's go, Art.
Aw. How big?
All right. Let's do some trig.
Let's.
You guys pumped for trig?
Oh.
No. If you need to reference a unit circle, because I'm going to give you some trig on your assignment. If you need to reference a unit circle, please do. Please remember that the x value at any point is the cosine, and the y value is the sine. So if you need to reference a unit circle, please do. I don't mind. Okay, let's do the definite integral from pi/2 to pi.
Let's.
Of 3 sine theta plus cosine theta d theta. So again, this is asking us what is the exact area underneath the curve or above the curve if the curve's below the x-axis really. So basically the area from this function either down to or up to the x-axis from when x is pi/2 to where x is pi. If we get a positive answer, that means the majority of the area, if not all of it, was above the x-axis. And if we get a negative answer, that means the majority of the area, if not all of it, was beneath. So it just depends on your function, but this will always yield the correct value. All right, so we need to take the antiderivative. What is the antiderivative of sine? Actually, first off, is this continuous?
Sure.
Well, of
Yes,
course.
trig.
Yeah.
So sine and cosine are continuous everywhere. The trig function that's not continuous everywhere would be tangent because that has asymptotes. It's sometimes undefined. But sine and cosine are continuous everywhere. They just look like roller coasters that keep continuing. All right, so sine of theta, what is its antiderivative?
Negative cosine.
Good. Oops. So it's going to be -3 cosine of theta.
Right.
Remember, the derivative of cosine is negative sine. So the derivative of negative cosine would be sine. I'm just kind of dismissing the 3 because it's not really that important. It just stays. Okay, how about the antiderivative of cosine?
Sine.
Fine.
Nice. Okay, we want to evaluate that from pi over 2 to pi. All right, pi over 2 is up here. Pi is here. This is the coordinate point 0, 1. This is the coordinate point -1, 0. Again, if this is not familiar to you, please just Google a unit circle. Makes your life a whole lot easier. All right, so we want to first evaluate this at pi, our top limit of integration, our upper limit rather. So -3 cosine of pi plus sine of pi, and then subtract at our lower limit, which is -3 cosine of pi over 2 plus the sine of pi over 2. I'm writing a lot more. I'm not doing a lot of this in my head, so you guys can just see it all. But essentially, you don't really need this step if you just want to find it directly. Okay, the cosine of pi, cosine is your x value at any radian or any angle on your unit circle. So that's -1. The sine of pi is 0. So this would be -3 times 1 plus 0. So that's just -3. I'm sorry. What did I just do wrong there? The cosine of pi is -1. My bad. There we go. And that is a plus 0, so I didn't write anything. Okay, minus the cosine at pi over 2 is 0. So this term goes away. The sine at pi over 2 is 1.
Wait, you have a times in the first one? Shouldn't that be a plus?
Yes. No, it shouldn't be, because this is -3 times the cosine of theta, and the cosine of theta is -1.
Okay.
I said theta. I meant pi. I'm sorry.
Sine pi is 0, right?
0. So I just
Okay.
opted not to put plus 0. Yeah.
Gotcha.
Okay, then over here, this term goes to 0, and the sine of pi over 2 is just 1. So inside this parenthesis, it's just 1. So we end up with 3 minus 1.
2.
That equals 2.
Good job, guys. I'm proud of you. Again, calculator, make sure you're in radian mode. You should always be, honestly. You don't need to use it for anything else. Okay, it's 1:34. So I have three more examples for us. All right, I'm going to let you guys try one on your own. So the integral from 1 to 4 of 5x to the 4th plus x minus 1 dx. I want you to do this A, by hand, and B, on a calculator to check your work and make sure you get the same thing. If you need to do small pieces, parts of the algebra on your calculator, that's fine. I just want you to show the work algebraically.
Okay.
Okay, we should get 1027.5 or whatever that is as a fraction. Your calculator should also give you that too. So if you're plugging something, again, that's more complicated into your calculator, what I highly recommend doing, and just, we've done this throughout the year, but I'll just repeat it, is plug this function in for y1.
Okay, I didn't do that.
Yeah, I think that that's probably a better bet. So if you plug in that function for y1, it kind of alleviates any errors that you could potentially make. I mean, this one isn't too complex of a function, really. Then, once you have it in for y1, which I do, if you go to Math 9 from 1 to 4, and then just type in, instead of having to type in the function, you just hit alpha trace and select y1. That makes it a lot simpler. So alpha trace y1 dx, and you'll get the 1027.5. That's what I recommend doing, especially if it's an FRQ or something that you have to use the same function multiple times. Instead of having to type it out a million times, just have it in this y1.
Can't you also do like graph it and then like have it fill in?
Yeah, for sure. So if you want to do it like that, you can. So if you go to your graph and graph it, the issue with that is I feel like you have to like mess with the window and stuff.
Yeah.
But actually, you might not have to. I don't think you need to see the entire thing to do that. So yeah, you could still graph it and then hit second trace number 7 and do it that way. All right, I have one more that is algebraic, and then I just want to recap something geometrically from the other day. So last algebraic example. The integral from -2 to 3 of 1/4, we'll do 3x minus 5 quantity squared dx. So when you have a constant out in front, like the 1/4, that 1/4 does not need to be messed with until the very end. I highly recommend getting it out of the way. So you really could write this with the 1/4 completely in front of the integral. And I feel like that alleviates a lot of issues. Now, then you're left with this, which you cannot directly integrate. Ideas on what we need to do there to be able to integrate it.
Put them together.
Yeah, multiply it out, right?
Yeah, that's what I mean.
So yeah, so it's 3x minus 5 squared, so it's times itself. So if we multiply 3x minus 5 times 3x minus 5, we'll be left with 9x squared minus 30x plus 25, just from foiling it out, dx. So you do have to do that in order to be able to integrate it, just because this entire thing squared is just not going to work for what we know so far how to do. Once we get into fancier integration and use substitution, it could work, but this is definitely the way to go. So you just have each individual term. And again, this 1/4 out in front, it's not going to matter until the very last step when you just multiply by 1/4. I recommend doing it that way because you have way fewer fractions to deal with. Imagining distributing a 1/4 through, that's so messy. So we can just integrate it from here. So in the next line, we'll have I'm just going to keep the 1/4 out in front so I don't forget about it. But I'm going to put the rest in brackets to deal with that first. So we'll have 9/3 x cubed, so 3x cubed. Please do not write 9 over 3. That is unnecessary. Then in the next one, we'll have 30 over 2, x squared. And then lastly, we'll have 25 over 1, I guess, x to the first, so 25x. And I'm putting that in brackets because that's the only thing we need to evaluate at 3 and -2. Again, you don't need to worry about this 1/4 at all until the very, very last step. So we are only plugging in 3 and -2 here. So when we plug in 3, I'm going to do as much as I can in my head real quick here. So we'll have 3 cubed, 27 times 3 is 108. And then minus 3 squared is 9, 15 times 9 is 135. Oh, 27 times 3 is not 108. I'm sorry, guys. I had a brain fart. It's 81. Plus 25 times 3 is 75. Okay. Then we'll subtract and plug in -2. When we cube -2, we'll get -8 times 3 is -24. When we plug in -2 here, squared will be 4 times 15 is 60, so minus 60. And 25 times -2 is minus 50. Whew. All right, so this is -134 in here. And the other one is 21. So 21 plus 134 is 155. All right, that 1/4 still was out front the whole time. I promise it was there. So there it was. And then we still had the 1/4 out front here. And then we still have to multiply it by 1/4 or divide by 4, same thing. So you can write it as a fraction or a decimal. Either way. Sorry that one was algebraically messy. I honestly just made it up because I remembered I wanted to show you this idea and I forgot about that. So that was our last example made up off the spot. I hope the algebra looks okay. Okay, real quick, before I let you go, I just want to talk about one more thing. And that is something we talked about on Monday. So I'm just going to do a quick sketch just to give you an idea. I'm not actually going to do a problem, but we're just going to talk through something real quick. So remember, integrating is just finding the area underneath the curve of an infinite number of rectangles, basically. It's the Riemann sum idea, but done in a calculus way. So if we have some function, I'll draw a function in red. And it's geometric, basically. And that function is f of x. And I'll put some values here. So -2. And then this is a hole in the function. So just to talk about a couple different things, right? If I asked you, you know, this is geometric. I'm not giving you any value or any like actual equation for f of x. It's more conceptual and geometric. So if you were asked to find the integral from 0 to 3 of f of x, let's think about what that means. That means find this area underneath the curve from 0 to 3. Well, the way I would do that is split it up. From 0 to 2, it's a rectangle. Or a square. There we go. And then from 2 to 3, it's a triangle. So essentially, you would just have to find the area, right? So this area is 4, and this area is 1. So this would just be 5. So you can do that. Where could you not integrate through, like over what number? Or what x value could you not integrate over, basically? 6, yeah. I realize I did not ask that question very well, so I'm sorry. But we could not integrate if this interval here of our limits of integration contains 6, because we have a removable discontinuity there. We have a hole. So again, you need to be continuous.
Wouldn't it not affect the area though, because it's just a point?
Yeah, the idea is that you can't ever, this one does seem like it wouldn't affect it that much. You're right. I see where you're coming from, but it technically does because, you know, math is all weird, and technically this point doesn't exist. So we can't be directly like under it or ever get to it. That's why. A better example for discontinuity would be like this, if I were to draw to see this better. Like, let's say you had a jump discontinuity.
Okay, I'm in class.
Like, you couldn't do that over 6 because you wouldn't necessarily know what height to go to, really. I see where you're coming from, Ryan. That's a pretty valid question. But since that point doesn't exist, there's technically not area like directly beneath it, if that makes sense. So we can't ever quite get to it because it doesn't exist. So any discontinuity, you can't integrate over that value. Jump, removable, or asymptotic, infinite, rather.
Already.
Yep. And then one last thing before I let you go. If you were to find the area underneath here, technically area is positive, but since it's underneath the curve, that value would be a negative value. So just be careful when you are integrating geometrically. If you're below the x-axis, that value is negative. Okay, I need to let you guys go. It's 1:50. If you have questions, my office hours today are in 10 minutes. Take care.
Thank you, Ms. Tomas.
You're
Thank
welcome,
you.
Mark. Bye-bye.
You're gonna email us the assignment.
Yes, I'm gonna do that right now.
Cool.
Okay.
Cool.
Have a good day.
You too. Good questions, Ryan. Bye.